Moving on to the pure capacitor circuit, where we connect a capacitor to this empty space over here, we will see that if our current is designed to be varying with this fashion over here, I naught sine omega t, if our current is varying this way, and we measure the potential difference across the capacitor, we'll find that the voltage of the capacitor is varying with this fashion over here. It'll be varying in the sine omega t minus pi over 2 fashion over here. So if we see the current and the voltage, they are not in phase like just now. They do not have the same phase omega t, omega t. For here, you see that the current is varying with omega t, whereas the V here, there's an omega t minus pi over 2. So we can see clearly from here that there's a phase difference between the sinusoidally varying current and the sinusoidally varying voltage. So we see here that's negative pi over 2. So this negative pi over 2 is what we call as the phase difference. So this phase angle here, sorry, not phase difference, phase angle. So this phase angle here, we write it as negative 90 degree or negative pi over 2. So what does this phase angle means? Phase angle is the angle of the V0 phasor with respect to the I0 phasor, which we will describe in the next slide over here. But never mind. We just need to know that for this case, you will see that it's negative 90 degree. So from here, you will know that actually V is lagging I by pi over 2. Because you see this negative sign here, this negative sign means by this equation here is lagging this equation by 90 degree. The equation with negative pi over 2 is lagging the equation with no negative pi over 2. So we know here that V is actually lagging behind I, and by how much? By pi over 2, which is 90 degree. The lag is carried, the information of lagging is carried by this negative sign here. So you don't need to write the negative sign again here, because the lag here already carry the meaning of negative sign. Okay, so through our lecture, we have already done some derivation, and at the end of derivation, we find out that the equation of the V is actually varying with I0 over omega c sine omega t minus pi over 2. So by comparing these two equations here, we are able to know that V0 is actually equals to I0 1 over omega c. So this is the equation that relates between the peak voltage and the peak current. Of course, if you translate into RMS version, there's another RMS version, which is VRMS equals to IRMS 1 over omega c. So these two equations are valid, and you want to transform between one to another, you just use this equation over here. Okay, so we have get this equation V0 equals to I0 1 over omega c. So what's the importance of this equation here is, for us, when we are dealing with AC circuits, we are very particular with the ratio of V0 to I0. We always want to know what is V0 divided by I0 is. Okay, so from there, if you see this pure C equation, we see that V0 divided by I0 will be 1 over omega c. And because this value is important, because it's the ratio between V0 to I0, we give it a name. We give it a name as capacitive reactance. Okay, so how much does it react to the voltage? And as an effect, you produce how much current. You can think of it that way. Okay, how does it react to the voltage? Okay, so from this case, you see that our capacitive reactance is equals to 1 over omega c. So if you have a greater capacitance, you have a smaller capacitive reactance. If you have a greater angular frequency or frequency, okay, you have a lower reactance. Okay, so let's think of a situation here. Let's say if you put a capacitor over here, and you have an accumulator. This accumulator can produce an AC current, right? Let's say you're producing a current with very high frequency. So if you produce a current with high frequency, what will happen is the denominator for this fraction here will be high, because if F is big, then 2 pi Fc will be very big. If the denominator is big, then we know that the capacitive reactance will be low. So a high frequency current will actually cause the capacitive reactance to be low. So if the capacitive reactance is low, then it means we bring down this 1 over omega c. Then what will happen is you might cause an increase in current flowing to the circuit. It's not usually the V0 that change, because V0 actually depends on your accumulator. Let's say your accumulator is like your power supply in your lab. You set it to 10 volt AC circuit. So this is the peak voltage here is 10 volt AC circuit. You fix it already. So now if you change the frequency of the AC circuit, you run through the circuit, then let's say you bring up the frequency, then this reactance will get lower. Then the effect will be the current flowing through the capacitor will be larger. Okay, this is fixed. You reduce this by increasing frequency, then as an effect you have greater peak current flowing through the circuit. So this is how this capacitive reactance work in a circuit. It controls how much it controls the ratio between V0 and I0. Okay, so we always call this kind of situation because it allows high frequency to have great current. It causes low frequency to have small amount of current, because low frequency will increase reactance will decrease the current. So high frequency, greater current, low frequency, less current. So in that case, we can say that we call it a high pass filter, because higher frequency information can cause greater current, whereas lower frequency information will cause a smaller current. So you can say the high frequency information pass through in a greater magnitude compared to the low frequency information. Okay, that's why we call it high pass filter. It's not really in your syllabus, but it's a very, very important circuit component in AC circuit. It helps us to filter out low frequency. Okay, just like if you are using speaker, if you have bass and treble, right? Let's say you want to remove the bass. Then high pass filter will be a very good option, because bass are lower frequency. You want to filter out the lower frequency. So that's the purpose of high pass filter, and it can be achieved through the use of capacitor in AC circuit. Okay, so let's move on to discuss question about pure capacitor. 100 microfarad capacitor is connected to an alternating voltage of 12 volt. Okay, so and frequency is 50 hertz. So in this case, you are actually connecting a capacitor and you connect it to an alternating voltage. Okay, something like this. We know from here that the alternating voltage is 12 volt, but they didn't really specify whether it's peak voltage or it's RMS voltage. So for these kind of cases, we usually just assume it to be RMS. If they didn't specify it's RMS or peak, we think of it as RMS, because we usually describe AC circuit in terms of RMS. We don't usually describe it in terms of peak. So if they just write 12 volt, then it should be VRMS. So the VRMS is 12 volt and it has a frequency of 50 hertz. And we know that this capacitor has a capacitance of 100 microfarad. Okay, so now the first thing that they ask you to calculate the reactance of the capacitor. We know from just now, reactance, in this case capacitive reactance, is X subscript C. So we know that is equals to 1 over omega C. Well, we don't have omega, but we know frequency, so it will be 2 pi Fc. So in this case, it's just a matter of substitution again. 2 pi, the frequency should be 50 hertz. The capacitance should be 100 times 10 to the power of -6. So if you multiply all these things together, what you will get will be 31.83. You might be wondering, what is the unit for capacitive reactance? I didn't really mention it. But if you look back to the previous slide, it's V0 divided by I0 that equals to I1 over omega C. So if we know that V0 divided by I0 here is equals to R, and R has a unit of ohm, then we know that 1 over omega C is also V0 to I0. So 1 over omega C must also have a unit of ohm. So we know that the capacitive reactance is 31.83 ohm. The second thing that they ask for is calculate the current in the circuit. So how are we supposed to calculate the current? We have to remember that the relationship between VRMS, between reactance and current. So the relationship, we know that reactance is always a ratio between V and I. So in this case, we can apply it to be the ratio between VRMS and IRMS will be equals to X subscript C. So what we want here is IRMS. They didn't mention they want peak current. So if they didn't mention peak or RMS, we assume it to be RMS. So in this case, it will be VRMS divided by XC. So we know that VRMS here is equal to 12 volt. And the capacitive reactance we calculate from just now is 31.83. So if we substitute everything together, you'll find out that the answer is equals to 0.38 ampere. Okay, so this is the root mean square current of this capacitor, root mean square current flowing through this capacitor over here. Okay, so let me try to again explain this thing. If one day you happens to have not 50 hertz current, 50 hertz alternating voltage, let's say you have 100 hertz alternating voltage. In that case, you need to sub in 100 over here, right? You sub in 100 over here, you'll notice that this XC here will be smaller than this value here. Okay, most probably half of this value over here. Then if you sub in a value that is half of 31.83 here, you'll find out that the current will be twice of 0.38. So it will be 0.76. So do you notice that bringing up the frequency actually causes greater amount of RMS current flowing through the circuit. So that's why we call this kind of situation, we call this kind of circuit a high pass filter, because it allows higher frequency to generate more current. Lower frequency will generate a smaller magnitude of RMS current or peak current. Okay, so that's all for example 8.